And so with that, I am very excited to introduce our speaker for today, Nathalie de Leon, who comes to visit us from Princeton Electrical Engineering. So I think Nathalie is one of the few people that knows chemistry and materials physics and quantum devices really well. And so she has made sort of amazing progress in both, NV diamond, but also in her spare time revolutionizing superconducting qubits. And so she's really a unique person in the field, able to tackle the quantum devices and materials challenges of these systems at the same time. And I hope she's going to tell us fun and interesting things. Oh, I forgot to say, her PhD was from Hong Park, and she was postdoc with Misha. She's done lots of good things, and will tell us more.
All right. Well, thanks for the invitation to come. It's always fun to visit friends at JQI. And Alicia warned me that this is a very question-happy crowd, and I am happy to field questions in real time, but I will just give you the disclaimer that all of the new results on how to make a millisecond scale coherence time transmon qubit are at the end of the presentation, and it's a 65 slide talk. So if you want to learn about that, okay, you got to give me the space. All right. So as Alicia mentioned, I have kind of a broad range of things going on in my group. About 2/3 of the group works on color centers in diamond, mostly for quantum sensing. And the efforts are, ooh, I don't like that. The efforts are roughly divided into, about half of the group is using NV centers in diamond for quantum sensing. I have a small effort trying to work on core technologies for long distance quantum networks. I have a new burgeoning effort actually on materials growth together with the Princeton Plasma Physics Laboratory. So this is a very quick plug for it. We have started growing quantum grade diamond at scale. We have 4 reactors sort of right off the bat, and an element 6 reactor, the first jailbroken element 6 reactor arriving this year. Actually, it's sitting on the loading dock right now. And then I guess it's my spare time. It was supposed to be an eccentric hobby, but it's now 1/3 of my lab working on a very different system, which is new material systems for superconducting qubits. So I'll just tell you, one story about this, and then another story about this at the end. So the physical platform that we work with for quantum sensing is the nitrogen vacancy center in diamond. I'll just go through this very briefly, but basically, if you take a diamond lattice, punch out 2 carbon atoms, and put in 1 nitrogen, you get these very deep electronic defects that are really mid-gap. And diamond gives you a large enough headroom with its very large band gap that you even have electronic orbital excited states that are also very deep electronic defects. So to sort of first order and even second order, this thing really acts like a trapped molecule. And you don't have to really think very hard about the surrounding lattice and the itinerant states associated with the band edges. Okay, the reason that there are so many groups that are working on this one color center in diamond, enough that I took the list off of the bottom of the slide because it was like a political liability, is that this defect just happens to have extremely long spin coherence times, even at room temperature. You have a spin lattice relaxation time of about 10 milliseconds. The coherence time is just limited by how well you can isotopically purify the surroundings. So it's sort of easy to get a millisecond, even at room temperature and ambient conditions. And also there's a really convenient way that, oh my gosh, I really hate this laser pointer. For optically manipulating and measure the spin. Also in ambient conditions, if I just take a green laser pointer and shine it on the NV center, I can optically pump down into ms equals 0. And if I just ask kind of how many photons do I get back, I have a spin-dependent intersystem crossing that will take me to this shelving state if I'm in one of these spin sublevels. So I basically get an optical readout of the electronic spin state just by counting photons with off-resonant light. So I can do this as, I can measure, for example, the Zeeman energy of the spin resonance and use that as a local measurement of the magnetic field. And I have nice kind of coherent control over the spin even at room temperature.
So before you go away from that one, back to the previous slide. So you got this nice Robbie flopping that's pretty much 100%. So what was going on with the fluorescence only changing by
Oh, a little bit. Yeah. Well,
what else is
right. No, so it's just you just rely on sort of the lifetime of this dark state and all of your branching ratios. So this guy lives for about 150 nanoseconds. My excited state lifetime is 12 nanoseconds. And my kind of spin selectivity, I think, is only 3 to 1 or something. So all of that sort of conspires to give you something like 30–40% contrast. Yeah. Okay, so there's now, dozens of groups around the world who are trying to use this as a basis for nanoscale sensing. The reason that it's a really interesting platform is you have these very long spin coherence times, so you can, do all of the nice tricks that we know how to do to get very sensitive magnetic field measurements. And then because this thing is really a single spin, it looks like a true point defect. The extent of the wave function is less than a nanometer. Then that means that I can have extraordinarily large magnetic field gradients around this single spin and use that to distinguish between, for example, protons in a protein that's decorating the surface. I can do a very small volume liquid NMR. And then I would say the bulk of the field is really focused on kind of this task, which is trying to use it as a tool for condensed matter physics. So, and that's what we have been focused on for the last couple of years is how do you really use this as a quantitative tool for condensed matter physics? And I think it's worth looking just really quickly at, a comparison between NV centers and other techniques to see what kinds of physics we can learn that are usually inaccessible. And I think most of the field has sort of been focused on this axis, which is that at DC, it's a very good magnetometer. So I can use an NV center as a replacement for a squid or some kind of magnetic force microscopy probe. And you can get very, very high sensitivity, but most importantly, extremely high spatial resolution because I can get within nanometers of this sensing target. However, I think there's actually a lot of opportunity in trying to think about the NV center as a dynamical probe. And in particular, because this is a spin and I can manipulate it and drive it however I want, I can now use it to look at noise. And in general, it's a lot harder to measure noise. Usually people are doing things like global transport or scanning probes. And it's very hard to get access to a lot of these dynamics. So if we think about this in frequency and length scale, NV centers are very good at nanometer length scales, which are really hard to reach otherwise. You can go out to microns and tens of microns with optical microscopy very easily, and we can get these extraordinarily high sensitivities even over a fairly large bandwidth from kilohertz out to gigahertz without doing anything too fancy. And this is nicely complementary to other techniques. If you think about how do I study dynamics usually, I can do optical pump probe kind of types of spectroscopy, but those tend to be diffraction limited. So you're talking about micron scales. And then how exactly to translate that to a sensitivity is always unclear, right? Because you need to figure out some matrix element and that's going to be very material dependent. So the nice thing is the NV center is really like a quantitative probe where we know this is the magnetic field. So as long as I can connect that magnetic field to some phenomenon, then I really measured it. And then similarly, there are things like dynamic neutron scattering, which gives you access to angstrom scale kind of length scales and very high frequencies like terahertz frequencies. But this is a very different regime from where we are. So I think there's a real opportunity space to try to learn new physics that are otherwise inaccessible with the current probes.
我出来了，
Yep.
我操，今天这不对劲呀！我操，
Oh, nope, that's not for me. Could you mute yourself, please? Okay. So what we've been thinking about is, how do we develop tools to really understand condensed matter phenomena? And a lot of the work in this space, there's been some beautiful work over the last, let's say, 10 years. For example, using the NV center as a DC probe to look at current through Biot-Savart, or you could just look at magnetic structure directly, like these are vortices, threading through a little disk of superconductor. And then there have been a few studies trying to use the NV center as a probe of noise. So this is a really nice example out of Misha's group from a few years ago, where they took a single NV center, fabricated a graphene device on top of it, and then just by doing relaxometry, so looking for noise at like gigahertz frequencies, they were able to see this excess noise when you were far away from some contact, which they attributed to this somewhat exotic electron-phonon coupling. So these are all really nice, but when I go down the hall and talk to my condensed matter theory friends, they don't really think about life in these terms. Like, what magnetic field do I measure when I'm at this offset distance? What they like thinking about is dispersion and transport and order parameters. And in particular, they really, really like thinking about correlation functions. And this is often like the best way to characterize some phase transition or some many-body phenomenon, is thinking about like the two-point correlator as you go across some critical point. So a natural question is, do we have a sensing modality that more directly measures some of these parameters? And correlation function seems like an easy thing to try to do. So let me motivate this a little bit more concretely. So let's imagine that I have a bunch of NV centers sitting underneath some metal that exhibits ballistic transport, and I have these electrons, rattling around with some characteristic inelastic mean-free path. If I asked each of these NV centers, what do you measure? Then each one would tell me something very boring. They would say something like, I see Johnson noise, it looks white, it's related to the temperature. But now if I instead ask, okay, if I take these two NV centers, is the noise that you see correlated? And then I ask that of every single pair, then you can imagine that the ones that are close together compared to this mean-free path are going to say, yep, we see correlated noise, because always the same electrons that are transiting both of us. But if I now look at this as a function of inter-NV separation, I'm going to get access to something that's like a spatial structure function of the noise, which would otherwise be hidden. Okay, similarly, yeah.
I mean, we think of it as a magnetic field sensor. So you're already thinking about a current, and this is
Yeah, it's just BO sub R. Exactly, it's just current noise. Similarly, if you if you look at sort of the dynamics of type 2 superconductors as you go through their phase transition, what you get is sort of the admittance of magnetic vortices, and BKT is like epsilon away from BCS theory. It's like not that hard to write down. But there have been very, very few quantitative tests of the fact that what you should first get are vortex-anti-vortex pairs. And then these things should sort of diverge from each other. And the reason is these are really hard to see normally. They're dynamical objects. They have many different length scales. It's a magnetic dipole. So if you're just doing magnetic sensing, you won't see it. But as long as I can get really close, this is now a two-point anti-correlation in the magnetic field at some characteristic length scale. So if I could get access to that correlation function, I could see this physics really nicely. Okay, so we wrote a review paper for Nature Reviews Physics, and now we have all these beautiful images that we can put in my talks. You have to name things. So we called it nanoscale covariance magnetometry, and everything I'm going to talk about was led by Jared Rovney, who's a postdoc in my group, and it was done in collaboration with Shimon Kolkowitz, who's now at UC Berkeley. Okay, so the setup is I have two NV centers. They're each looking at some correlated noise that I'm interested in. And then they also have some uncorrelated noise from like local nuclear spins or paramagnetic impurities. I'm going to do something very simple, which is I just do a Ramsey on both NV centers at the same time. They accumulate phase due to the environment. And then I map the phase to a population. And then I read out the population as a total number of photons. Okay, and at the end of each of these experiments, I just write down how many photons I get. And then now I just have arrays of numbers associated with each NV center, and I just compute a classical correlation between those two arrays. That's it. Okay. And then because these are spins, I can do whatever I want in this Ramsey. So I can now do spectroscopy of the noise by using different kinds of NMR pulse sequences, everything that we've known how to do for decades. So that sounds very easy. The reason that nobody had done it or even thought about it is that this correlation is very, very hard to measure. So we have this underlying phase distribution that we really want to measure, but on top of that is quantum projection noise, which says that I'm not going to map this phase onto a population perfectly. But much, much worse than that for the NV centers is that we also have readout noise, which says that I don't even read out my populations particularly well. And one way to see that is because we rely on this very short-lived dark state for our readout, we actually get very, very few photons per shot. It's 0.03 photons per shot. People don't like talking about this because I can just take a measurement every microsecond and average like crazy and get these, beautiful Nature paper figures or whatever. But this readout is extremely low fidelity. And for conventional magnetometry, it's fine because I can average. But now if I want to see a correlation, it's sort of like seeing a coincidence between these two traces, and the probability of that happening is very low. So the remedy is that we have to come up with higher fidelity readout. And one way to do that is by doing a spin selective ionization of the NV center that maps the spin onto a charge state. And then we're very good at reading out the charge state because those just emit in completely different optical bands. So I can get very high readout fidelity, and you can see now that I get lots of photons per shot, and then maybe I have a shot at being able to measure this correlation. The way that you should actually formalize this is by plotting some minimal detectable signal as a function of experiment time. So this is, for some amplitude of noise, how long would it take me to measure it to get to a signal to noise ratio of 1? If I had quantum projection noise limited readout, to get to a nanotesla would take me something like 10 seconds. With this conventional shelving state readout, it would take me 1,000,000 seconds, which is impractical and, most importantly, an unacceptable fraction of a PhD. So fortunately, with this enhanced readout, like spin to charge conversion, we can claw some of this back and get down to something like hours of integration time, which is not a fun experiment. I will say it's really unfun, but there's no other way to get access to these kind of 2-point correlation functions at nanometer length scale. So we're sort of not competing with anything. Okay, so we went out to experimentally implement this. And conceptually, this is very straightforward. I just have two channels on my confocal so that I can address 2 different NV centers and collect photons from them simultaneously. And then we turn on the correlation finding machine, and we immediately saw a lot of correlations, and none of them were spin-spin correlations. And the reason is that if I just do this to my optical table, that also gives me correlated photon counts for both of my NV centers. So we had to spend a lot of time sort of hunting down all of these different sources of noise. I'm very confident, actually, this crowd would kind of enjoy this story. The very last step was that Jun Yi told us, you know what, I bet your optical table has a touch in it. And I said, that's nonsense, because I can see that it's floating. I push on it and it goes, and he said, no. If it's ever lost air and you didn't rebalance it, then it might be touching somewhere. And then sure enough, we go down to the lab and just did this, and we could see. and that was it. So anyway, in the course of all of this noise hunting, I'm confident that we now have the world's quietest single NV center measurement by a lot, because it's sort of what it takes to be able to measure these correlations. But now we can just do it. So here's 2 NV centers in confocal microscopy. You can still, if I bin the data as if NV1 is dark or bright, as NV2 dark or bright, you can see like a very faint checkerboard pattern that comes from the background correlation. But I turn on some shared noise and you see it pop out nicely. And then one nice trick is that because these are spins, I can also do this trick where I prepare them on opposite sides of the Bloch sphere, antipodes, and then see this correlation flip. And we indeed see that checkerboard pattern flip. And then we can do spectroscopy to see this noise, and we indeed see this little peak that's associated with the bandwidth of the noise, and an anti-peak that is the mirror image when we do this in anti-correlation. So this gives us confidence that we're really looking at spin-spin correlations. Okay, so what can I do with this in the condensed matter context? One idea is with my single NV centers, I go do a coherence measurement. And then, maybe I see a bunch of dips that I convert into some spectral noise density so that I can see what all of the different peaks are. And then if I look in correlation, maybe only one of these things was due to shared noise. So now I can take my noise spectrum and start labeling the peaks as either correlated or uncorrelated as a function of NV-NV distance. So this is the experimental implementation of that. Here's 2 NV centers where they each had 2 narrow peaks in the noise. This peak turned out to be from some weird higher harmonic of the nitrogen nuclear spin, so it is not shared between the 2 NV centers, and we only see one of them show up in covariance. There's another kind of interesting regime where you have very strong white noise that is shared between the 2 NV centers, so I just turn on a very strong noisy tone so that their coherence decays very, very quickly. And then out here in the noise, you would normally say, well, I can't get any information out there anymore because their final phases are completely random. However, if I look in covariance, I can see a little NMR dip that shows up all the way out here in the noise. And the reason that this shows up is because even though the measurements out here, the measurement outcomes are random, they're always correlated with each other. Right, so they land on random places in the Bloch sphere, but they're always at the same place. So by looking in this covariance channel, I take out the common mode noise, and then I sort of recover some overall coherence of the system.
You said that you're looking at things as a function of NV to NV separation, but you described, picking a pair So then are you finding like another pair, or are you finding another one to correlate with
Yeah.
the one that you're starting with?
So what I've shown you here is like it would be impossible because I have these two different galvo channels, and then I've thrown out a bunch of my photons. So this is not a very scalable technique, because in order to find these different pairs, I would have to do this sequentially. But I'll show you in like 10 minutes, yeah, how we can actually scale up. Okay, there's one more trick, because these things are spins, which is that as long as I have independent control over my spins, I can do a measurement that reports on the temporal structure of this correlation by starting the clock on one NV center, waiting some time delay, and then starting the clock on the second NV center. And now the speed limit on this time delay is just the Rabi frequency, right? So I get this stroboscopic kind of fast picture of how much the relative phase accumulation changes between the two NV centers. This is an example of a shot-to-shot phase random signal, but because I'm looking in the stroboscopic way, I'm able to kind of reconstruct the coherent nature of the noise tone at, you know, nanosecond to microsecond timescales. Okay, so let me just quickly summarize this technique. So what I've shown you here is a method to measure anything that looks like a 2-point correlator in the magnetic field, anything that looks like BR1, T1, BR2, T2, with all that I've shown you so far is 100 nanometer to 100 micron length scales, but I'll show you 10 nanometers in a second. And the key is this is really not something that is physically accessible with any other technique. So I think it's a really exciting time for trying to understand things like critical dynamics in condensed matter systems, and look at some physics that has been otherwise resistant to traditional probes. Okay, so let me tell you a couple of technique extensions. Yes. Yeah, so let me talk about that right here. So everything that I showed you so far relies on being able to pick out the two NV centers optically, which means that they have to be separated by more than the optical diffraction limit, right? And then in terms of like how like the outermost kind of like what sets the other bound is basically what can you comfortably build your optical system around. So sort of 50 micron to 100 micron fields of view are pretty typical of high NA objectives. Okay. But so obviously there's a lot of condensed matter physics that happens below the optical diffraction limit that you would like to access, below about 200, 300 nanometers. So in principle, you should also be able to get covariance measurements if I just collect joint statistics of the two NV centers. So what that looks like is here's a doubly bright spot. There are two NV centers in there that are separated by less than 300 nanometers. But then now, their joint statistics are either going to look if they're correlated doubly bright, doubly dark, or anti-correlated, they should always be bright, dark, dark, bright. And then if they're uncorrelated, I should just get an average over those two distributions. So by looking at this, the variance of the joint distribution, I should get access to the covariance. So the reason that this doesn't work in practice is because any technical fluctuations, like the laser intensity changing, my table's still shaking, all of that stuff, is going to show up as excess variance in the single NV center statistics. And now I have no way of telling the difference between them because I've sort of thrown out my single NV data. So the remedy for this turns out to be like over half a century old. It's from NMR. And they use this trick called phase cycling, which is that at the end, I take my, my measurement and I just divide it into 4. And then basically at the end of each sequence, I either land the two spins on the same side of the Bloch sphere, opposite sides, same side over here, opposite sides in the other direction. And then I can just write down some arithmetic that cancels out all of the single NV center variances and just leaves behind the covariances and reports on them. So there's a little bit of overhead, but I can now, take this phase cycling as long as I have independent control and be able to measure these correlation functions very nicely below the diffraction limit. Okay, and then the idea is I can now combine this with sort of traditional super resolution imaging techniques like PALM, STORM, STED, which all actually work trivially and super easily with NV centers because I have coherent control over the NV centers, right? So instead of having to wait for them to blink, I can make them blink and then fit their positions. So I can figure out where they are and then do this kind of joint statistics covariance measurement. Okay, for experts in the room, this is actually a lousy technique because it relies on having independent control over the two NV centers, for example, by making them misaligned with respect to the magnetic field. And that tends to screw up a lot of your selection rules and really limit like how high in magnetic field I can go, for example. So what you would really like is a technique for being able to do this even if they are spectrally indistinguishable, which sounds impossible because to do the phase cycling, I have to be able to, move them selectively on different sides of the Bloch sphere. But here we have this neat little trick, which is that the natural abundance of carbon 13 in carbon is roughly 1%, which means that if I just take two NV centers that are very closely spaced and I just ask what's the probability that one of them has a carbon 13 that is strongly coupled to it, only one, it's about 90%. So almost all of these pairs have a random strongly coupled carbon 13. And we can see that when we do qubit spectroscopy, because if you just do NMR, we see this big bath that comes from, or this broad peak that comes from the incoherent carbon-13 bath. But then you also see this nice kind of coherent oscillation chevron pattern that comes from strong coupling to a single carbon-13. So I can now use this as a basis of kind of a funky gate, which is that I can conditionally spin flip one of my NV centers conditioned on the presence of a carbon-13. I actually don't care how it's pointing, but I just care that it exists. And then now I can use this as a basis for phase cycling and for two NV centers that are both optically unresolved and spatially unresolved. I can now do these covariance measurements. Okay, last trick. If I get these things close enough together, like within 20 nanometers, 10 nanometers, I can also just have them talk to each other via dipolar coupling. And then now, if they are, as long as this dipolar coupling is strong compared to all of your background decoherence, I can just make Bell states. So I make Bell states of my two NV centers and use that as a basis for sensing. So I guess if there are any NV people in the room, you would know there's a big graveyard on this topic. Because obviously we have a dipolar, you're going to try to do dipolar coupling. And there are a lot of people who have tried to make pairs of NV centers and use that as a basis for entanglement. And there have only been a couple of successful experiments, and they've really been built on like a single pair that somebody found in one magical sample, and then they went and published like 10 papers on that single pair. This is much easier to do, and I'll tell you the main ingredients are that we're very good at making shallow NV centers, and then all you have to do is do nitrogen molecule implantation, and then the two nitrogens will just land very close together, and then you have some finite, conversion efficiency of getting two NV centers. So I can say that in one field of view, usually what we find are something like 10 pairs, and something like one of them have this strong coupling. It's really not bad. And we haven't done any optimization. So here you can see that these two NV centers are strongly coupled to each other using double electron-electron resonance techniques. And now I can use this as a basis for preparing different Bell states. And my symmetric Bell states are now going to accumulate phase twice as fast from shared noise, whereas my anti-symmetric Bell states are in a decoherence-free subspace, so they should just not see the shared noise at all. And indeed, that's what I see here. My anti-symmetric Bell states don't see the oscillating magnetic field, whereas the symmetric Bell states accumulate phase twice as fast. And then what I can do is now use this as a basis for covariance sensing, because if I just now measure the states and then just take, psi minus phi or phi minus psi, then that difference just reports on the shared noise directly. And here, so let me just say as a slightly ranty thing, normally people sort of twist themselves into knots to try to show quantum enhanced sensing. And you work really, really hard to get your factor of root 2. So we get our factor of root 2, that is true here. But in addition to that, if you do a true end-to-end resource estimate, we actually gain by our readout noise. Because now instead of having to do, two independent NV measurements and eat my readout noise twice, I just do a single Bell state measurement, and I only get penalized by my readout noise once. So I think this is one of the very, very few cases where we actually have entanglement enhanced sensing, and we didn't throw it all away in our resource estimation, state preparation, infidelity, and all of that stuff. So you'll notice this data here is actually much, much more beautiful than this data here, and that is just a reflection of this root 2 times 40 enhancement that we get in sensitivity. And you can also see that in this curve here, where this is now far below what we had before. I think there's like, I don't know if I've like fully committed to the sales pitch yet, but I think there's a sense in which if you want to measure correlations, the most natural way to do it is with a correlated state, that you shouldn't have been trying to do that with uncorrelated, intrinsically uncorrelated states anyway. Do you have a question?
Clarify, so say this is like square root over the standard function, like is that the correct interpretation or what's the reference point?
Yeah. So no. So the reference point is what would you do if the two NV centers were unentangled? And if we had quantum projection noise limited readout, then you would only get a root 2 enhancement. But here, because our readout noise is so bad, we get root 2 times that. So we actually, it's a funny case, but it's, I think, a genuine case in terms of being able to use these sensors practically. So I think it is one of the very, very few cases where if you ask somebody, okay, I have this task, I have a thing you want to measure. Would you rather your sensors be entangled or unentangled? And here I would rather they be entangled. So if I can do it, I would take this every time.
Sorry, that's a good question.
Yeah.
So big picture. So what are you actually trying to measure here? Is it just the absolute value of the field, time result field? What's the figure of merit increase?
It's a 2-point correlation function in the magnetic field. So it's BR1T1, BR2T2.
And these distances are fixed, right?
The distances are set by the NV
So you can't
distance.
actually change them.
Well, I can pick different NV centers.
I see. And what's the actual distance in number? Like
In this specific case, 6 nanometers.
Actually, I guess this sort of goes back a little bit of the basic quantum mechanically, these two operators don't technically compute.
Which two operators?
B R1 T1 and B of R2 T2 because they're different times.
Right, yes.
So which time ordering, and this is physically, I guess, related to can you also pick up like this correlator technique quantum mechanically has a noise part and a susceptibility part.
Mm-hmm.
So which one is it? Is it just purely the noise somehow you anti-symmetrized or symmetrized it or?
It should just be the noise
Okay, so
part.
not the susceptibility or the. Yeah,
Yeah, it is just the pure magnetic field. So then if you actually want to map it into anything else, like some particular bit of many body physics, I think that's where exactly what kernel you use is going to change, right? Like, is it some underlying magnetic ordering or is it some current? And then you're either using fluctuation dissipation or you're using, whatever to try to actually back out what your physics is.
But I guess so I should think of it as a symmetrizer if I think in terms of operators. Like it's
As in, like, it doesn't matter in what order I measure.
yeah, like is it B R1 T1
Uh,
plus
Yeah. Okay. What I can say is the NV centers don't care. And then the open question is whether the condensed matter thingy that you're looking at cares. Right? If we could see something that's not symmetric, that would also be kind of intrinsically interesting.
sorry, just the time here is measured like in seconds.
Yeah.
That's the relevant time scale.
Yeah. Experiment time, actual time on the clock.
Because I can't imagine any condensed matter experiment where seconds are relevant time scale.
No. This is integration time. So this is how long on the clock do I need to keep on averaging? Right. All experiments incur this. People do STM, neutron scattering. You have some time to average down your signal. Yeah. So the relevant timescale for dynamics is how fast is my Rabi frequency, which is like gigahertz. So it's still kind of slow compared to a lot of physics, but there's a lot of physics that is fine around there.
Now, how do you determine the distance? You said that, like, I think it was 6 nanometers. Is this done by the super resolution thing?
Yeah.
Not one of those other tricks that you were using that got the strong coupling with the isotope with the carbon-13.
No. Yeah, it's just
not using all of that to tell you how far apart they are.
No, because that carbon-13 is only strongly talking to one NV center, not both of them. So there's no way to get the relative distance that way. Yeah. Okay, so going back to Bill's earlier question, these measurements are very slow and sort of intrinsically unscalable because if you have to put in a beam splitter, and 2 more channels, then you're just throwing out a lot of photons. So what you would really like to do is just collect signals from all of the NV centers at the same time. And in principle, neutral atom quantum computers have already shown us the way. So what we've done is built the back end of a neutral atom quantum computer and the front end of an NV cryogenic confocal microscope. So we have one of these very low readout noise cameras, a wide field laser, and then a spatial light modulator for being able to pick out which NV centers to address. This was all led by Kai-Hung Cheng, who is a student in the group. So what we do is just collect photons from many NV centers at the same time. This should be a video. And then as you go through the magnetic resonance, you should see these little things blink off. And we can collect from, hundreds of NV centers at the same time. So we can sort of drive them and then see them all sort of turn on and off. We can get lots and lots of ODMR spectra simultaneously. And thanks to the magic of these very low readout noise EMC CDs that have only been on the market for the last like half decade or so, we only pay a penalty of about a factor of 4 or 5 in our readout noise for doing this. So we can measure hundreds of NV centers at the same time. We only lose a factor of 5. So you would totally take this trade as long as you can afford the camera. Okay, so we can use this as the basis for looking at spin dynamics across many NV centers. So this is just the sensitivity. We can look at T1 and do relaxometry. And then I promised you that we could also measure correlation functions. And the cool thing is that if I measure n NV centers, I now get n choose 2 correlators. So I can actually get a crazy amount of data just from one of these acquisitions. The real problem is that to get this high readout fidelity, I need to do the spin to charge thing. And that is very, very power hungry. So I can't just do wide field, illumination to do this ionization. So that's where the spatial light modulator comes in. So I put my orange light behind the SLM, and then you can see that I just pick which NV centers I'm going to address and ionize. This is probably too much in the weeds, but what we're able to do is take advantage of, the specific camera statistics where we operated in this thresholded mode, so that we don't incur a bunch of added readout noise, but it doesn't really matter. In the end, what we're able to do is very nice charge state readout and then pretty good spin to charge conversion. And this appears to just be power limited. So as we split our laser into more and more beams, we get more and more readout noise. So there's a remedy for this that I'll talk about in a second. But using this, what we're able to do is now multiplexed covariance magnetometry. So this is 4 NV centers where we're able to see, we're able to address all of them and then plot correlations between them. So we start to get these correlation maps. And as I said, our readout is only limited by the ionization power. So we now have a 100 watt, 604 nanometer laser sitting on the table. It's a pulse laser, so it's 100 watts over just a few hundred nanoseconds. They did not build this laser for me. 604 is twice 302. So this laser exists for ytterbium, and all we needed was just for them to get rid of the last second harmonic generation step, but it's very convenient for us. So with this 100 watts, we should be able to get to hundreds of NV centers sort of easily. Okay, the one very last thing about this, which is that I showed you a bunch of correlation functions. They're all kind of, they're roughly correlated and anti-correlated where you expect, but can we actually learn quantitative things about the underlying noise? So this is an example where we have a current carrying wire. We are looking at NV centers over here and NV centers over here. And then, with the right-hand rule, what you would expect is that these guys should all be correlated with each other and they should all be anti-correlated from here. And if I plot all of those correlation functions, you see qualitatively the right thing, right? They're anti-correlated with NV5 and then all correlated with each other, but there's all this like variation. So where's that variation coming from? And do we have quantitative understanding of all of it? And so the idea is if I can just measure each of my sensors separately, then I can get their readout noise parameters, their coherence, all of that stuff. And then make a prediction of what this covariance should actually look like, and then convert this into a reconstructed correlation. So here, now instead of plotting this Pearson correlation, I'm truly plotting BR1, BR2. And I'm able to really capture, other than this one NV center, or this one 2-point correlator, very well, what this should actually look like. Okay, so we think that this is going to be a powerful methodology for really reconstructing the noise for unknown systems. I'm just going to skip over this, but we've been working hard on device integration to try to understand different systems. And let me just leave you with like a very brief outlook, which is that, I think there are a lot of systems where the traditional probes, they tell you a lot, but then they can be either missing things or giving you a somewhat messy measurement. So this is a 2D magnet. This was all done in collaboration with Abe Pasupathi's group, where we're looking at chromium, sulfur, bromide. It's one of these layered materials that's anti-ferromagnetic. And then if you just look in DC, you see this stray field. And if I ask a very simple question, which is like, what's the nail temperature? When does it go from anti-ferromagnetic to paramagnetic? I get this kind of messy answer with a span of like 10 degrees. But now if I look in noise, then what happens is that you get these large fluctuations near the critical point. Their correlation length scales diverge. And I see this very sharply peaked signal in noise that allows me to pin down the nail temperature to about an order of magnitude, even 2 orders of magnitude, better precision than the traditional DC measurement. So we're now starting to look at more speculative unknown materials like tantalum cobalt telluride, which is this weird itinerant antiferromagnet that Leslie Shoup's group grows. And here we see really nothing in the static B field pictures, but when we look in noise, we can kind of see a dip around one of the phase transitions that you can see in neutron scattering and other probes. Okay, I'm going to totally change gears. So if anyone has NV questions, speak now or forever hold your peace. Or you can wait until the end, or we can
May I
talk at
ask a
lunch.
question? Sorry,
Yes.
I was a little bit sick, so I'm asking question online. It's Mohammed.
Hey, Mohammed.
So I hope I didn't miss it. When you mentioned this massive measurement, it was very impressive, and it is
Mohammed, you
locally-
cut out a little bit.
Can you hear me now?
Oh,
Do you hear me?
okay.
Can you-
Maybe I can catch you at the end.
Yeah, yeah.
Dependent entities, or it's a many body system itself with its own
Independent.
And why?
Yeah.
How do you know?
Well, they're like microns apart from each other.
Did you just say the distance was, I mean, I'm sorry, I can't reconcile these two statements. You said,
So the overall image with hundreds of NV centers, those are all at the, if you can see them, they're separated by more than the optical diffraction limit. And the optical diffraction limit is like 200, 300 nanometers.
I see, but you're trying to measure a correlation length and you.
Yeah, so and then
More than that.
that's right. So, but in order to do that, then you would have a single point that has two NV centers that are really close together. Well, they do if they get really close, right? So like 10 nanometers or something is roughly the, where we start to see dipolar coupling that competes with everything else.
And they end up close because that's the way you made.
Because that's the way I made them. Yeah, the probability of accidental inter-NV separations of 10 nanometers is so small that my postdoc wasted more time than I should admit in public because I said, we've got to find one. And yeah, so that turns out to be way too hard. You have to sort of intentionally create them really close together.
So when looking at those things, realizing that one eye is a very bad measure of this, it looks super Poissonic. That is the distribution of the ones that are optically resolved. It doesn't look like they're random.
Oh,
Is there?
I have never checked. It's a good question. I can come up with a few microscopic mechanisms for why it wouldn't be totally random, but I think it is random. I think it is random, but it would be it's easy to check with a bunch of image analysis. It's a good question. Okay, so superconducting qubits. So we are now living in an era of increasingly sophisticated and complicated superconducting qubit processors and other kinds of quantum processors. And there have been a lot of really amazing demonstration. I should probably replace this image with their more recent chip, but this is the Sycamore chip from Google, which had 50 qubits. They recently released Willow, which has like 100 qubits or something. And they've been able to do some, really interesting physics with it. And then very recently, some beautiful demonstrations of quantum error correction, even below the threshold. So this is all, I guess what I found myself kind of telling people is like the pace of progress here is really breathtaking. If I did apply to this place for a job 9 years ago, and and if I had gotten in front of this audience and said, I'm going to do quantum error correction, or I'm going to build a quantum computer, everyone would they would have said, you can't have a job. That's crazy. You're not going to do it in our life. You know, it's going to take a really long time. It was very, very out of favor. Nobody was talking about this a very short time ago. So the fact that now there are all of these demonstrations of like true quantum error correction is just amazing. I don't know how many of you young people know what time you're living through, but it's very, very cool. Okay, so this is very impressive. The thing that jumps out to me is that if you look at their error budget, their main errors are actually just related to single qubit operation. So we're not even hitting this limit where like really sophisticated like multi-body stuff comes up. It's really just the single qubits don't live long enough for us to be able to do the operations that we need to do to increase the depth of the circuit. So there's still a lot of work to be done on just improving the coherence of single qubits. So I can ask what has the score looked like on this front? And you can make sort of a Moore's Law style plot. This is out of a review paper that Will Oliver put together a few years ago, which is like lifetime versus year. And from the first Cooper pair boxes up to 3D transmon in 2011, 2012, there was this incredible march of progress. And I would say that essentially all of this came not from trying to get rid of sources of noise, but instead to change the qubit Hamiltonian to make it insensitive to those sources of noise. So it's sort of like instead of cleaning your room, I can just kind of throw a bunch of stuff on it and never actually pick up the junk that's on the floor. Okay, so that sort of petered out in 2012, and then there was just no progress for almost a decade. So despite lots of effort, lots of investment in academia and industry, no one was able to move this bound. All right, so we know a few things about this loss. The first is that this is all just dielectric loss. So I put it in a photon, the photon disappears. The other is that the losses appear to be related to surfaces and interfaces. So if I make the devices bigger, they get better up to some point. So this is Q versus like capacitor pitch width. And then the other is that the losses get a lot worse at low temperature and at low power. And this is why everyone in this field talks about so-called two-level systems. So what you have is some kind of saturable absorber that when I turn up the microwave power, I can saturate, or if I turn up the temperature, they can kind of thermally average. This is a plot of loss tangent, which is bad as a function of either temperature or microwave power. Okay, so what we're looking for are sources of two-level systems at surfaces and interfaces all across this device. And I'll say, actually, one of my formative experiences here was a review paper that I wrote together with Ben, who's in the audience, where we went and kind of systematically looked through literature and said, well, why do people actually believe the things that they believe? Can we really hunt down what people's reasoning is? Okay, so I started this collaboration with Andrew Hauk, who is an expert in superconducting qubits, and Bob Kava, who is a solid-state chemist who had never worked in this field before. And we just sort of sat Andrew down and said, okay, what are your devices made out of? I bet we can kick this. And this was the Hauk Lab qubit at the time, so it's very close to the IBM qubit. It's a niobium capacitor with an aluminum oxide Josephson junction all sitting on top of a sapphire substrate. And we immediately came up with two hypotheses for where this excess dielectric loss was coming from. My main hobby horse is I bet everything's just covered in junk. And if I just look up the loss tangent of hydrocarbons, or really anything that is amorphous, it's 10 to the minus 3. Your surface participation ratio is around 10 to the minus 3. 10 to the minus 3 times 10 to the minus 3 is 10 to the minus 6. There's your Q of a million. And that would also explain why everyone in the community was not able to do better than each other, because if they were all just covered in a thin layer of hydrocarbons that they had not removed from their fabrication, they would just be stuck at a million regardless of the underlying material that they're using. Okay, Bob pointed out, all right, so if we're going to clean off all of this stuff, you need this material to survive whatever is going on there. And let me tell you, niobium is like the worst thing I've ever worked with. And he, had all of this work from the 80s and early 90s in Bell Labs, where you could stabilize any stoichiometry of niobium oxide. You got a totally different stoichiometry depending on whether it was too humid in the lab that day. So he said, this is going to be just impossible to control because it's very chemically fragile. So we worked on a bunch of cleaning and substrate preparation methods, and then switched to a material that is much more robust to all of this cleaning. So we just figured out how to put tantalum down on sapphire and how to fabricate it. And as advertised, what we see is a very robust surface oxide that is sort of always 2 to 3 nanometers. It's a Mach-Cabrera oxide, which means that it's just limited. It will self-limit to this value. And we can do crazy things to it, like dip it in piranha, which is hydrogen peroxide and sulfuric acid, all kinds of acids. We can boil it in sulfuric, nitric, and perchloric acids for hours. And essentially nothing happens to the tantalum oxide. It always looks like this. But we can get rid of this sort of, contamination peak from carbon. And the end result was that we were immediately able to get to T1s of 300 to 400 microseconds right out the gate. So we're able to put our own little point on this plot. That was an improvement in, I guess this was 2020 now, of about a factor of 3 over the global state of the art. And here, this was not, we didn't change the qubit. It was vanilla transmon. We did nothing, but we did get rid, we actually cleaned our room this time, right? And we got rid of the underlying source of loss. Okay, since this work, it's been reproduced in many labs. There's a group in China that got to T1s of half a millisecond. The IMEC group in Belgium has done tantalum on silicon to get sort of comparable quality factors. And a tantalum qubit with a T1 of almost 300 microseconds was one of the key ingredients for Michel Devise' beautiful demonstration a couple of years ago of break-even quantum error correction with the GKP code. Okay, so now let me say a ranty thing that I think this audience will actually like, which is that in order to make progress on this topic, you cannot just try things and measure qubits. You have to do precision measurement. Nobody does it. Nobody does it this way. But what you really want to do is ask, what are all my sources of loss? How much does every single source of loss contribute? And only when you know that how much do you know what it is that you actually have to tackle. But in order to know how much, you have to define physics experiments that allow you to disentangle all of the different sources of loss and then quantify their contributions. So it's not enough to just sort of wave your hands and say 2-level systems. I have to say 2-level systems at this surface are 95.3% of my loss, and 2-level systems at this other surface are 4.2% of my loss. So that's this general project. So what we have been trying to do since that initial work is try to really figure out in a precision measurement sort of orientation what the different sources of loss are, and what we use are these resonators made out of tantalum. We can look at many of them at the same time. The measurements are very easy. We see a little resonance dip from each resonator, and we can do things like turn up the power, and we see that the internal quality factor increases as we turn up the power, consistent with 2-level systems. For the experts in the field, I will say that we've worked pretty hard on packaging and other things. So our high power Qs are now approaching 1 billion with a B. So this allows us to, it gives us a very low background loss that allows us to see very subtle changes from the underlying material system. And then we can take this one step further, which is to do this power dependence as a function of temperature, and we get all these wiggly curves. Okay, so each of these curves is from 1 microwave power, and we just sweep the temperature. And what you can see is that really dislike this pointer, at low powers, you get well-separated curve, or at low temperatures, you get these well-separated curves. At high temperatures, they all sort of collapse together. So what this is consistent with is I have a bunch of 2-level system related losses here. I have some equilibrium quasi-particle loss that turns on at appreciable temperatures of the critical temperature of the superconductor. And then I can fit this all to a quantitative model that takes into account the power and temperature dependence of 2-level systems, the quasi-particle temperature dependence, and then I allow for something that sets a ceiling on all of this that might be power and temperature dependent. So the key thing is what we see is a very nice fit. I guess here's the takeaway. It's a very nice fit to the data. Okay. It's a very simple model, but it's a very nice fit to the data. So I have a lot of confidence that I am capturing all of the right power and temperature dependence. And this is only something like 7 free fitting parameters. And one of those fit parameters is this guy, QTLS naught, which is a prefactor on the 2-level system related absorption. So in some ways, this is the closest thing that I have to a true material parameter in all of these measurements. It's like the linear absorption due to 2-level systems. So let's focus on that, because I can use that as the basis for actual materials comparison. So I can do things like make a bunch of devices, that have varying geometry so that I scan the total participation with the surface. And I can plot this QTLS naught, which is the inverse linear absorption due to two-level systems. And what I see is as I make the devices bigger, they get better, but maybe they kind of taper off at some point. So I can now start to compare different surface treatments, right? Like I etch it in acid and then see how much this changes. And indeed, what I see is that these things kind of nicely separate down here, which means that there's some sort of surface-related losses, but then they're all kind of mixed up here. So maybe there's something else that is not surface-related, right? I have two different sources of loss. So I can put a whole bunch of hypothesis testing, a lot of chemistry, a lot of fabrication of materials, and put it all together. And my overall picture of the world is that here's our current state of the art. We have some surface loss that looks like this. For the largest devices, there's also some bulk loss, and the only thing that can give me bulk loss is the underlying sapphire substrate. So it's all two-level systems, but I have two different sources of two-level systems. There's something at the surface of my device and something sitting in the substrate. I'm not showing you nearly enough data to justify what I'm about to say, but you can just trust me that we have a lot of it. And we're pretty sure this is the tantalum oxide. Okay, so the surface losses are all just tantalum oxide. Okay, so here's where we are. In some ways, this is a terrible world to live in because it means that your bulk losses and your surface losses are roughly equal contributors, and you have to combat both to be able to get your next improvement in the state of the art. And our packaging, again, is way up here, so it doesn't matter for all intents and purposes. Okay, so we've been working very hard on trying to disentangle these different sources of loss. So we're combining this two-level system analysis with a bunch of materials spectroscopy. We found sort of paradoxically that as you made the films really, really nice and improved their crystallinity, we actually introduced vortex loss because there's nothing pinning the vortices anymore. But the nice thing about this methodology is we could see it right away in the temperature dependence and sort of parameterize it away. And then what we've been working on is trying to get rid of this surface loss, for example, through noble metal encapsulation. So, one way to get rid of the surface oxide is to just use a metal that never forms a surface oxide, like gold or palladium or platinum. None of those superconduct. So there's no way to just switch to a metal that doesn't have any oxide. So instead, what we've been making are heterostructures of tantalum and noble metals, and then relying on the proximity effect to open up a superconducting gap in the noble metal. And somewhat surprisingly, that actually works very well. So we're able to suppress the surface oxide with just a few nanometers of gold, and we see very little change in the total size of the gap. Okay, but here's where we've been able to see the biggest improvement is by trying to tackle the bulk loss. So we just tried kind of the next obvious thing. I mean, we tried a lot of things, but this was the one that worked, which was to go look for an alternative substrate to sapphire. And what we found was a vendor that would give us very high purity, high resistivity silicon. We had to come up with methods for developing alpha phase tantalum without getting a bunch of weird interface states and like silicides at the interface that caused a lot of problems. And what we're able to see from the resonators, so the orange and the gray lines are from tantalum on sapphire, is that the surface losses are pretty similar. But we can see a lot of resonators that blow way past this bulk line for sapphire. So what that means is that we've been able to get rid of the bulk loss that we were seeing for sapphire by just changing the substrate. And we were able immediately to translate this to qubits with very long lifetimes. So our peak T1 is 1.68 milliseconds. A lot of people like to cherry pick a single time trace. So here is that same qubit over 88 hours. And we're able to see a T1 that's above a millisecond almost all the time, with a time average T1 of around a millisecond. And here's like every qubit we've ever made. So here's all our warts. All of our process development is here. The average quality factor is over 10 million. And then this is maybe slightly provocative, but there are a bunch of reports in the literature of kind of maximum Qs and then the time average Qs for best qubits. And here's ours in comparison. So it's a very large change in the state of the art. Okay, somewhat to our surprise, once we did this, once we had these very, very long T1s, we could also see that the junctions were now limiting our T2s. And in particular, we could make a lot of qubits that had very, very long T1s, but then the T2s were like a tenth of T1 or a quarter of T1. And there was an enormous amount of variability. We then spent a bunch of time trying to optimize the junction fabrication. I would like to tell a nicer story, but it was really just getting rid of like hydrocarbon contamination. It was very easy. And what we were able to do was switch from this old deposition chamber to this new deposition chamber with all of our best practices. And we're now able to get to T2 of between T1 and 2T1. This is just Haneko T2. So no dynamical decoupling or anything. Very easily. And I don't think I have, yeah, okay, I do have it. So then you can ask, well, what the heck is going on here? How come there are some that are still a little bit worse than T1? So when we go and do just spectral noise decomposition and try to interrogate the noise model of those qubits, what we find is a noise bath that looks like this. So it's pretty flat, and then we have a cutoff, and that cutoff is suspiciously exactly the same as our readout resonator bandwidth. So what we believe is happening is that we just have a little bit of dispersive coupling to hot photons in the readout resonator, and that gives you a little bit of this remaining T2. That's a very nice problem to have because there's an easy remedy, which is just like you detune away from your readout resonator a little bit more. Okay, and then what I would like to emphasize is that, again, vanilla transmons. We have sacrificed absolutely nothing in architecture or drivability or anything. So we just do minimal single qubit gate optimization. And what we find is a gate fidelity of 99.994%. So we're able to get sort of world record single qubit gate fidelities without having to pull any tricks at all. So I think there's still a lot of room for improvement on this front. Okay, and then we can stick our little tantalum on silicon transmon point up here, where we're now able to get to sort of these millisecond scale relaxation and coherence times. Okay, so just to conclude, we've seen now 2 big leaps in performance from relatively simple materials changes. I think there's still a lot more room to explore here. And the key ingredient is really doing this with a precision measurement mindset. We're able to first identify all of your sources of loss, triage and rank order, and then tackle the worst one first. But then this also means that you have to be very agnostic about what the source of loss is going to be. If you sort of see yourself as, I'm the kind of person who loves to measure 2-level systems, it could be that that's not your problem right now. And then, you have to spend a bunch of time on vortices for the next 5 years. And then once you get past that, then you can work on 2-level systems. So I think you have to come to the problem. The problem's not going to come to you is sort of one of the messages. Are we out of time? Is that what you're having? Okay. Okay. The other kind of message is that what we found is that material resilience is probably as important or maybe even more important than the underlying material properties. I think a lot of folks would have wanted to say, okay, just give me some set of desiderata for the material system, and then I'll like pick some, perfect handmade, hand-picked material out of the materials database. But here, what really mattered is I can dunk this thing in acid and it doesn't care. And that's a weird parameter space to be operating in that I think make a lot of material scientists kind of uncomfortable, because now what we have to say is, look, I need something that opens up the processing space for all of the gross stuff that we have to do this to get it into like a back end of line, processing on a 300 millimeter fab. And I think it's a very important criteria that, at least as physicists, we're not really used to thinking about either. The thing that I'm most excited about now is, these things fluctuate in time. We probably got to fix that. And ours fluctuate in time a lot less than other people's fluctuate in time. We have something like 20% variability. But I think it's clear that these errors are going to matter a lot, especially as you start going to larger scale processors. Okay, so there's a very large team to acknowledge. On the covariance sensing, that was all led by Jared Rovney. The multiplexing work was led by Kai-Hung Cheng and Zishan Kazi, and again, was all done in collaboration with Shimon Kolkowitz's group. And I should thank the Moore Foundation, the NSF, and others for funding. The superconducting qubit work it's a very special collaboration. Andrew's group, Bob's group, and my group are in a maximally entangled state. Like the students really wake up and go and hang out with each other and plan experiments together. It's not just like somebody makes the device and hands it off, and you could have done that collaboration by FedEx, but they're really truly working together. So it's been a real privilege. And the most recent tantalum on silicon work was led by Farideh Rami and Matthew Bland. And then there's, now a large team and a large set of alumni. And I should acknowledge the Department of Energy C2QA, which is one of the NQISRC research centers, which has really been a big funder of this work. And then more recently, some sponsored research from Google Quantum AI. And with that, I will stop and take your questions.
Run a bit long, so I think just a couple brief questions and then it's lunchtime. So I think Bill has had quite a few, so I think you're out.
Okay, thanks. Yeah, it's interesting work on TLSs. So, you were talking about the importance of the tantalum oxide, and you were finding actually, it was kind of interesting because back, maybe a decade ago, people were looking at niobium, titanium nitride, and also the substrate to air interface. So you switched to silicon. You did mention if you're doing an HF etch clean, if that's part of the process. You didn't say, you're mostly saying, hey, we were able to avoid looking at substrate to air interface surface loss.
Yeah,
so what's the story now after,
right.
in light of the previous stuff?
So it is all in the paper, which is on arXiv. We do substrate preparation to be able to remove the surface oxide before we deposit tantalum. And then you can ask, okay, this device is sitting out in air. How quickly does that surface oxide grow back? The answer is it's surprisingly slow. Like if you leave it out for 2 months, you grow back about 2 nanometers of oxide. So we just measured that and said, how much excess loss do you get from that 2 nanometers? And the answer is none at all. That the points are perfectly overlapping with the no silicon oxide part. So with the scatter of our data, I can say that the the surface losses associated with silicon oxide are at least less than 10% of the total surface losses that we see. And then when I say that it's all the tantalum oxide, my loose evidence for that is that we did all this stuff on the crystallinity of the tantalum. We've changed this heteroepitaxial boundary so much. We went from sapphire to different sapphire surface preparations to silicon. We grow the oxide. None of it matters. So I think the fact that we can go from polycrystalline to these oriented grains to single crystal and none of it matters means that the whole game, at least for now, 90% of it at least, is the tantalum oxide.
On the surface of that, not in the interface.
Yes.
Nothing at the interface.
Yeah, there's nothing at the interface.
Thank you for the remarks. Can you share a little bit about, do you have any understanding about the frequency distribution of the TLS? Have you ever measured any different frequency of the cavities? Have you tried ever characterization for different frequencies?
Yeah, so we haven't done a lot of like strongly coupled TLS stuff because honestly, I think it, well, it matters now for the time variation, probably. But I think in terms of total T1, it's clear that we were mostly dealing with all the TLSs sitting in the capacitor, which you wouldn't have seen with that technique. But I think there's some indirect evidence that I can say, right? So if you look at the power dependence, it's clear that we have a bunch of stuff that's on resonance with the qubit, but that and with the resonators. But if you look at the temperature dependence, it's not very power dependent, which means that you must have a very broad band bath. Right. So everything is sort of consistent with the picture that everyone else has developed, which is that you have an almost white profile of TLS frequencies, which is like pretty weird when you think about it. Like if you just try to write down any atomistic microscopic model for what could be giving you that, it's pretty strange. I mean, I think the probability that like it's all just Phil Anderson style amorphous oxide stuff is high. That's probably it. But maybe we'll find weird stuff once we get past this first layer.
I think we've run fairly late, so there will be student tea with Nathalie this afternoon, and then lunch.